Okay, this is the fall 2012 final from the Physics 1 lab. It's first a multiple choice. For a block resting on a flat surface, the normal force is equal to the weight of the block. That's B. You can see that if you have a block on a flat surface, I have two forces on it. I have the weight of the block, and then I have the normal force. Since it's not accelerating, I can say that the normal force minus the force weight equals ma. So then a is equal to 0 if it's not accelerating. So Fn is equal to Fw. All I've done here is I've just applied Newton's second law. Which of these forces provides the centripetal force for a ball being twirled in a circle? That's going to be the tension force. I have a ball on a string and it's traveling around. The string applies this tension force, which causes it to move in this circular path. What is the net torque acting on this board? All right, I have two torques. Let's see, this torque causes a counterclockwise, so it's going to be a positive torque 1, I'll call it. This force causes clockwise motion, so it is a negative torque. I'll call that torque 2. So torque 1 minus torque 2 will be the net torque. That's going to be 2 newtons times 2 meters, force times the moment arm. The moment arm is the distance from where the force is applied to the axis of rotation, minus 4 newtons times 1 meter. That's equal to 0, so the answer is B. What is the x-intercept? The x-intercept is the point where the line crosses the x-axis. That's at x equal -2. It's also the point when y equals 0, if you want to think about it in that way. Material with a higher specific heat is not necessarily more dense, not necessarily a bigger mass, is not warmer to the touch necessarily. That depends on, the temperature of the object, like has it been heated or cooled or whatever. So C is the right answer. It requires more energy to raise its temperature than for a material of the same mass with a lower specific heat. We can see that with this. Q equals mc delta T. This is my specific heat. This is the amount of energy required to raise it a certain temperature. So if C is bigger, that means it's going to require more temperature to raise it by delta T. So C is the right answer. Measure the length and diameter of the provided cylinder. So our cylinder would look like this. You would use your caliper to measure the diameter and then also the length. You can find a simulation of this online if you go to the course website right here, physics/physics103, and go to the vernier caliper simulation. You can find one that's very similar to ours. You can change this and move it around. The only difference here is this is given in millimeters. So for example, instead of 52.90, ours would read 5.290 because centimeters, you just move the decimal place one place to the left, right? So you can find that there. There's also a little video of me just sort of going through the tutorial for how to use these. So that's probably a good place for you to practice that, or of course you can practice it in the lab as well. All right, determine the mass of the aluminum cylinder with the provided materials. So what we would do is we have a meter stick here. You would balance it at the center of mass, and then you would hang your masses here and here. We could call this R1, this R2, and then you would say that this would be your cylinder over here, and this would be some known masses on your mass hanger. You could take the mass of the clamps as well, which you would need to know, and then you could just balance the torque. Say that torque 1 on this side is equal to torque 2. That's going to be M1G times R1 equals M2G times R2. The G's cancel. M1 is made up of the mass of the hanger plus the mass of the clamp plus the mass of the load. So you need to find that total load times R1, which you would measure, divided by R2, which you would measure, and that will equal to M2. We did this in 2 different labs, so if you need practice with this, please let us know. What is the density of the cylinder? Well, let's see. We have this aluminum cylinder. We have its length and diameter, and now we have its mass. So to find density, it's just going to be mass over volume. We first need to find the volume of a cylinder. A cylinder looks like this. It's a circle that's extended over a certain length. I'll call this h. We know its diameter, so we can find its radius, which is just 1/2 its diameter. And the volume of a cylinder is pi r squared times h. Right, that's the area of a circle times the height of the cylinder. And then once you find its volume, you can find its density. As we set up in lab, card of mass in, blah, blah, blah. Let's see. Oh, so this was the work lab that we did. You need to know how to draw the force vector diagrams. It was an inclined plane. I'll call this angle, let's just say it's 30 degrees. Or you could call it, we'll call it phi. All right. I have this cart that's on it, and it is moving up the inclined plane with a constant velocity. That means that the acceleration equals 0. And now I can draw my forces. I have several forces. I have the normal force, Fn. I have the weight, Fw. And then I also have the frictional force, which is going to act opposite. And that's going to be Fk. Let's go ahead. I think this was all that was required for this, but let's just go ahead and label all the forces on our vector diagram. So here's Fn, here's Fk in this direction, and then we had Fw. Now this angle is going to be theta, which is equal to 90 minus phi. In this case, it's going to be 60 degrees. So you need to label that properly. And then you can find the x and y components of this vector. Fn, Fk, Fw cosine of 60, and Fw sine of 60. So I've resolved those vectors, and now you could apply Newton's second law as well. Okay, so on this plane, it moves a distance of 0.3 meters. I want to find the work. So I had this system that's described in this problem. I have this. It has a mass hanging over here. The total mass is 0.2 kilograms. It's moving up the inclined plane, and I want to know what work it's done. Now, this mass moves a distance of 0.3 meters. So I can do a couple of different things. One, I know that there is a force applied here. Actually, no, let's see. I misread the problem. We're looking for the work done by the mass hanging on the pulley on the cart. So I want to know what work is done by this mass on the cart. And that's just a simple thing. It's the force, which is the force is 0.2 kilograms times g, which is 9.8, times the distance over which it acts, which is 0.3 meters. So remember, our work equals force times displacement. This is my force. It's the weight of the object times 9.8 times 0.3. Let's see, that's going to be roughly 2 times 0.3, which is 0.6 joules. Now, if you had additional information, you could also determine what is the new energy of the cart. But in order to find that, we would need to know what is the kinetic friction, and then we could say that the net work done by on the cart is going to be this 0.6 joules minus the kinetic friction times the distance over which it acts. And we did that in lab as well. And that'll give you the new energy of the block. All right, draw the vector diagram, label the appropriate angle theta, write the equations. Okay, so here we're just supposed to draw the vectors, resolve them, and and apply Newton's second law. The sum, or just show the sum of the forces. I'm going to actually do it from over here. It's a little bit easier. And my tension, Ft, well, it's not easier, but it's, I'll show you, Fw. Here I have Ft. This is my angle theta. That's going to be relevant. And then I have Fw here. All right, and then I resolve this. So the reason I drew it on the left side is that so Ft is positive. So it's in that first quadrant. I have Ft sine theta, Ft cosine theta, and I have Fw. And then the sum of the forces in the y are going to be Ft sine theta minus Fw. And this is going to equal to the mass times the acceleration in the y direction, which is equal to 0 because it's not accelerating in the y direction. And then the sum of the forces in the x is just going to be Ft cosine theta. And this is going to equal ma. This is my centripetal acceleration, however, so Ft cosine theta is going to equal mv squared over r, and that's what we'd be looking for that final answer. All right, what are the period and radius of motion? Well, to find the period, I just take the time from peak to peak. That's from 5 to 10, so the period is 10 minus 5, or 5 seconds. And then to find the radius, I take the distance from here to here and divide it by 2. So that's going to be 3 minus -3 divided by 2. This is going to be the radius of the motion. That's 6 over 2, which is 3 meters. Or you could take it from the origin, and that's also 3 meters since it's centered around the origin. Determine the spring constant K from the graph. The equation of the line is there. So here, first I want to just draw a line. You'll use your ruler to draw a best fit line. And then I pick 2 points on the line. Let's see, I'll pick this point. And pick this point. Now there happens to be a data point there, but I only picked that point because that line was, that data point was actually right on the line. And then I can find the slope. My rise is 0.4. My run looks like 0.1. So my slope was 0.4 over 0.1, which is 4. And my y-intercept, I don't think I need it, but let's just go ahead and show you. My y-intercept is 0.2, it's right here. And I am looking for the spring constant K. Now I have this equation, T squared equals 4 pi squared over K. That's mass of the load plus mass of the hanger, plus 4 pi squared over K times the fractional mass of the spring, times F times the mass of the spring. So this is my y variable, this is my x variable, here and here. So my slope is equal to this. So my slope equals 4 pi squared over K. My slope is equal to 4. So those cancel. So K is equal to pi squared, which is approximately equal to about 9 or 10. It's newtons per meter. All right, you combine 50 grams of copper shot. Oh, by the way, on this one up here as well. Also, you could find the fractional mass of the spring. You would say that the y-intercept is equal to 4 pi squared over K times the fractional mass, fraction times the mass of the spring. And then you could just plug in our 0.2. Our K is 9. F, and then whatever the mass of the spring is, it would be given, or you could measure it. And then you can solve that for F, just as we did in lab. You combine 50 grams of a copper shot initially at 100 degrees Celsius with 100 grams of water at 20 Celsius. Is the final equilibrium temperature. What is the specific heat of copper? All right, so I know that Q is equal to MC delta T. And I know also that the sum of all Q in a closed system is equal to 0. So if I put in copper shot into a container of water, the Q of the copper shot is going to go down. It's going to be negative, but the Q of the water will go up. It's going to be positive. So those two are going to be equal. Whatever energy lost by the copper shot is going to be gained by the water. So I'm just going to write it this way. I'll say that the Q of the copper shot is going to equal the Q of the water. What I've done here is I've said that QH2O minus Q copper is equal to 0. I do the sum of the Q's is equal to 0. Q of H2O is positive, Q of copper is negative, and so I can write it like that and then say that they're equal. All right, and then it's just MC delta T for both of them. So it's the mass of the copper, which is 50 grams, times the specific heat of copper, which we want to know, times delta T. It was initially 100 degrees Celsius, and then it goes to 30 degrees Celsius. So it had a change in temperature of 70 degrees. This is going to equal the mass of the water, which is 100 grams. It's the specific heat of water, which is 1, times the change in temperature. It starts at 20 and goes to 30, so it's going to be 10 degrees Celsius. So let's see. C of copper will be 1,000 divided by 50 times 70. That's going to be 3,500, which is some value. All right, data were taken for the surface area of the sphere, which is represented by this equation. I want you to graph the data and determine the value for pi, and then compute the percent difference. So I know that area was 4 pi r squared. So if I plot area versus r, it's going to be a parabola, and that's not what I want. So what you want to do is plot area versus r squared. You'll get some data. There's some amount of scatter to that data. It's not going to be a perfectly straight line, but then you'll fit a straight line to it. You pick 2 points on that line, find the rise by looking over on the y-axis, find the run by taking the difference in these two numbers on the x-axis. The slope will equal the rise over the run. And then we plotted a on our y-axis, r squared on our x-axis. So 4 pi is going to represent the slope. So whatever this slope is, let's say it's equal to 12. I think it actually is pretty darn close to 12. Then I would say that 12 is equal to my slope from the equation, which is 4 pi. And so I would get pi equal to 3. And then you wanted to find the percent difference. It's going to be the calculated minus the actual absolute value divided by the actual times 100. So that's going to be 3 minus 3.14, the actual value for pi, divided by 3.14 times 100. I don't have a calculator, but that has some value. It's small. And that's all. There's the equations that you needed. Notice that I listed the volume of a cylinder a little bit differently than it's listed here. I listed the volume of the cylinder as pi r squared times h, but here it was listed in terms of the diameter. So since the diameter is d over 2 squared times h, so that's pi over 4 d squared times h. So those are the same, except I used L here instead of h, but they're the same formula.